Okay, I've started the recording, so anytime.
Okay, so why don't we start? So today's speaker is Doug Rowland from NASA Goddard, and he's the chief of the laboratory for ionosphere, thermosphere, mesosphere physics. And he also serves as a GDC project scientist, and his research has primarily focused on sounding rocket measurements of magnetosphere, ionosphere, thermosphere coupling using double probe electric field instruments. And when not working, he enjoys board games and karaoke, and he's also working on a novel based on the life of Catherine Barton, intellectual socialite and Nisa Isaac Newton. So today he is going to present on GDC. So go ahead, Kevin.
Thanks, Nick. I saw your Isaac Newton picture over here. I was just wanting to take a picture so I could have that for documentation. Anyway, thanks a lot for inviting me, Nick and Cheryl, for taking care of everything here. I'm just very happy to be here. I've been to NCAR a couple times, but not a lot, so I'm very happy to get to know you guys a little better. I'm here just to talk about GDC. We had a little meeting, a little informal meeting about GDC earlier, but that was more about how to maybe collaborate a little better. This is more about what GDC is, for those of you who may not be familiar. GDC is the Geospace Dynamics Constellation. It was a mission that was recommended by the 2013 Heliophysics Decadal Survey. And I know actually people in this room were involved in that process. Thank you. And thanks also for contributing to this decadal survey, which is just getting underway. That's how we get these missions going, how we get the big efforts in model development, ground-based development, and just science culture and science development. So this decadal survey is extremely important, and you can see it here. One of the fruits of the last decadal survey is now coming to fruition. So of course, I have a huge science team that's working with me. This is not me. This is about 65 people, plus the efforts of the decadal survey, plus the efforts of the engineering team, and so on. So I just didn't have room to list everyone, but I'll give you an indication of who's involved in a bit. And feel free to, how do you guys usually do? Just interrupt with questions, or what's your preference?
Either way.
Feel free just to speak up, raise your hand, whatever. It's no need to be formal. So I mentioned GDC is a mission from NASA. It's the next Living with a Star mission. For those who don't know NASA speak, we have major programs in the Explorer program, which is undirected missions. They can study anything that's a heliophysics topic. So ICON, GOLD, AW, EASY, these are some of the Explorer missions. We have solar terrestrial probes, which include multi-scale, Magnetosphere multi-scale OMS mission, the IMAP mission, the dynamic mission will be an STP mission. And then we'll be Living with a Star, which is really interesting because that's science that also has societal relevance, societal application. Of course, all of our work, of course, all of heliophysics has societal implications, but the emphasis on Living with the Stars is to really find those intersections where we can really do a lot to advance understanding of space weather, understanding the impacts on technology. And so Living with the Star missions have included Solar Dynamics Observatory, Van Allen storm probes, and Parker Solar Probe. And that's a solar mission, magnetospheric mission, a solar wind mission, and now we have GDC as sort of the fourth major mission of that one. We're currently in the formulation phase, and for those who don't know what that means, just basically means we're studying the mission, trying to get all of our plans together, understand what the science is going to be, make sure the science is equal, the science return equals the money we're spending. You know, that we're not kind of spending too much to get too little, or we're not biting off more than we can chew. But there's a long process for that, and that takes a few years. And then after a while, we'll be in the design phase, the build phase, the test phase, and following the science. So we're in that early phase where we're just kind of still laying out the pieces and trying to make sure all the pieces fit together. We're selecting science team. The headquarters is selecting science teams, selecting instrument teams, and then NASA Goddard, which is the implementing group, is things like selecting a spacecraft and selecting all the different pieces and trying to glue it all together so it makes it coherent. GDC consists of 6 spacecraft. I didn't put that here, but it's making multi-point measurements of energy inputs into the upper atmosphere and ionosphere and how that upper atmosphere and ionosphere responds. And it's a plan for a 3-year mission to explore the upper atmosphere. Also, I guess I would say that in addition to being this Living with the Star, it also forms a critical component of the Heliophysics Science System Observatory. And that's sort of the group of all of the heliophysics missions together give you the full picture as much as we can from the sun all the way to the mesosphere and out to the rest of the heliosphere. So GDC will perform a major role there, which is looking at this, I would say, up until only recently, fairly ignored region of geospace, at least by NASA. I think NSF and NOAA have done quite a lot in this region. But NASA had done a lot of experimentation here in the 60s and up through 1980s. We had the TIME mission, and then recently we had the ICON and GOLD missions and AWE. But up before that, there was a long dearth of missions from Dynamics Explorer 2 till TIME, with only URs kind of filling that middle one. So this is sort of an important mission. I think it's sort of rebooting a little bit NASA's investment in the ionosphere thermosphere system. And part of the excitement is that this region is what we call the heart of geospace. If you want to talk about space weather, it's all well and good to say the sun is emitting CMEs and the sun is emitting flares and so on. But those don't matter unless they impact human technology or human society. So while we care about our robotic missions throughout the solar system, we care about our astronauts and so on. A lot of the impacts, especially the big dollar impacts, are those that happen here in the upper atmosphere and by extension, the ones that kind of propagate through to the ground. So I'd like to just impress upon you, this is maybe a region that has been understudied, but its time has come really to get the next observations. I mentioned the Heliophysics System Observatory. This is sort of just a sketch of the current version. It might even be a little bit out of date. We keep amazing. NASA headquarters has done a lot of work in the last 10 years based on the input of the last decadal survey to increase the flight rates. For a long time, we had a very stretched out flight rates. We weren't doing that many missions. But of course, the system science benefits when there are multiple missions up simultaneously making measurements. And so, for example, ICON and GOLD are recent additions to this list. Punch is not yet launched, but is one of our next missions to study the solar corona. Tracers is going to launch to study the Earth's cusp, and so on. So really a lot of effort here to add to this and kind of flush out the different pieces to try to trace the energy all the way through from left to right, and also to trace the energy from the surface of the Earth back up. There's a lot of energy there through the lower atmospheric force. So those two pieces are kind of the areas we're looking at, and using this fleet of spacecraft to study them. GDC, for those of you who are maybe not in the ionosphere thermosphere world, if you're in magnetosphere or solar physics, I'm not sure how broad this group is, but I'll just put a quick note here, is that the region of the atmosphere that we're talking about is right around the International Space Station. This is a region where we have coexisting ionized and neutral gas population. The thermosphere is the hot extension of the atmosphere that is extremely hot, up to hundreds or several thousand degrees, and is not well mixed chemically. So that's the region of our atmosphere which is very different than the atmosphere we breathe. It's also very less dense than the atmosphere we breathe. So if you imagine standing on the Earth's surface, where we are, we're a little higher here. The density in Boulder is a little bit lower. But as you go up and up in your airplanes in the stratosphere to the mesosphere and beyond, the density falls off exponentially, but there is still atmosphere there. And importantly, that's a region where things like satellites that are in low Earth orbit experience orbital drag due to the wind resistance, the air resistance of plowing through that gas at 8 kilometers per second. And space station, for example, would deorbit within months to a year or two if it was not reboosted periodically with engines. GDC is going to fly right to this region. Why this region? It's because this is the region where there's sort of the strongest and most complex interactions between the ions and neutral gases. At low altitudes, the neutrals, we don't understand the neutrals fully, but they dominate, and we get that sort of one set of regimes. At high altitude, we don't understand that either. That's the ionosphere and the magnetosphere where the plasma physics dominates. But a really interesting region that we really don't understand is this region where those two groups come together, and there's a lot of interesting physics and chemistry there. So just to sort of orient you, we're studying this region around 300 to 400 kilometers, right where the peak of the ionosphere is at nighttime, and right where the combination of the density of the thermosphere and the ionosphere is kind of both large enough to have interesting effects. So GDC measures two things. It measures the energy inputs that come in primarily from the magnetosphere. The magnetosphere sends electrical currents along the magnetic field lines. Those electric currents drive electric fields. They drive energetic electron and ion precipitation. And those particles and those electromagnetic inputs rain down to the atmosphere, primarily at high latitudes, but not only at high latitudes. And they can drive energy change in the upper atmosphere. And then we want to look at the responses. Once that energy comes in, it's dissipated in a variety of ways at a variety of altitudes, latitudes, and so on. And the dissipation can be single step, where we just drive some heating or some ionization, or it can be an interesting multi-step process where you might drive heating that drives differential upwelling of different gases, and that has all kinds of feedback effects in the ionosphere and so on. So there's all these kind of complex responses that happen when you start putting this energy in. They can take place in terms of the bulk motion of the gas. You can start stirring up the ionized or neutral gases and drive winds. You can heat the gas, and the gas can have 3 different temperatures. Electrons, ions, neutrals can all have different temperatures. And you can change the chemical composition as well. And so by modulating these 3 responses in the ions, neutral gases, you can get a really broad variety of response. In particular, we're going to be measuring things like electrical currents, chemical composition, the wind flow, the heating, and so on throughout the entire globe. Really is where GDC is focused. The decadal survey in 2013 led to another report, which is this. NASA likes to do these in stages. They like to get the broad brushstrokes from the decadal survey that say this is the general science topic we need. This is the general way in which you should approach it. But then to really focus in and decide exactly what science you want and kind of scope out how much it might cost, they will typically commission a science and technology definition team. And that team is a team of something like 20 people, experts in the field, who go off, each with a certain sub-expertise, and together they collaborate and write a report that describes the very details of the science, why it's important, what you can do, what you should do. And this was done in 2018 and 2019. I think people in this room were involved in that. Thank you for your service. And it was a really nice report. You can download it. I recommend if you haven't seen it. And they suggested 2 goals for GDC. They suggested goal number 1 is look at this high latitude energy input region and see how that high latitude region takes in energy and how it responds to variable solar wind magnetosphere force. Then goal 2, so that's looking at the high latitudes in the north and south hemisphere. Goal 2 is understand how internal processes redistribute that mass momentum and energy changes that are input at high latitudes. So you kind of think of goal 1 as where's the energy coming in and what is it doing at high latitudes, and then the second piece is that system science. Once the energy comes in, it doesn't just stop. It generates waves, it generates winds, it generates chemical changes that extend to all latitudes, electric fields at low latitudes, changes in the plasma density, and so on. So really a global mission and looking at these 2 different goals. And so GDC basically focuses on making direct space environment measurements of all these inputs and responses. That's different from a mission like ICON or GOLD, which really has direct space environment missions on ICON, but they're really focused on the remote sensing. Remote sensing can really give you an interesting picture either for 2-dimensional spatial variation or for time variation if you're watching a certain region, or for altitude variation. Those are things that we aren't doing with GDC. And the reason is because those images, they need to get done, and they need to get done for various reasons. But we also need to have sometimes these highly resolved local measurements, because those images can't give you everything you need. Typically, the images can be used to tell you something about maybe the wind, something about the chemical change, something about the plasma density, maybe the temperature. But you're not going to get things like the detailed mass composition of the gas. You're not going to get the detailed electric field that's happening there, the electric currents and so on. So you kind of really need both approaches. You need the direct measurements that give you those very finely resolved, comprehensive, all the state variables get measured. And then you really need the remote sensing as well to get that big picture, the space-time variation, the altitude profiles. And I'll tell you how we're going to do that here, even though GDC is not making those second class of measurements. I'll tell you that in a second. So we're focusing on these direct space environment. We're basically flying along at 350 kilometers. We're measuring the local environment. We're not measuring below us for the most part. We're just measuring where the satellites are. But we're doing that from an array of distributed platforms. So we have 6 spacecraft. They're all identical. They're all making the same measurements. And by doing that, you can then get back some of the stuff that you lost by not taking pictures. You can get back measurements of the spatial gradients, the temporal rates of change, all those things. So that's where we kind of come back to this idea of kind of advancing over previous missions, which basically had a single point, and you never knew what was happening east and west of your orbit. You didn't know what was happening 5 minutes later. That's the limitation of a single spacecraft. With multi-spacecraft, you can understand spatial gradients and temporal rates of change, and that's really what GDC is about. So when you want to look at these spatial changes, you have 3 options. You can either do the remote sensing image, but as I mentioned before, that doesn't give you all the state variables that you might need. So if you're going to focus on direct input measurements, you can go brute force. you can have a very dense array of sort satellites, kind of like the Starlink constellation, that would just blanket the Earth with satellites, and everywhere you'd be measuring everything all the time. And I can see that might be possible in the future. Starlink is showing the way on how to build multi-thousand spacecraft constellations. They're not yet to the point of being able to host sophisticated instruments and sort of make them work properly, but it might be possible in the future that we would have the capability of these very dense arrays observatories. Given current technology and sort of budgets, we're going with sort of in the world of telescopes, you might think of this as an aperture synthesis or interferometric approach, where you have 6 satellites, and then by having the different baselines, changing their baselines, you can resolve different features, and you can resolve much more fine scale features than you could with a single or smaller number of spacecraft. And because we can't look at all baselines simultaneously, and look at all spatial scales simultaneously, we call this a modal mission, where we are in different modes throughout the phase of the mission. We start together, spacecraft very close together, we're measuring very small scale features, kind of like, you can see some smaller scale features in these images here. And then as the mission goes on, we expand the separation between the satellites until they're covering the very largest scale features. And so in the same mission, year 1 might be small scale, year 2 is medium, and year 3 they're looking at the global picture. Now you're missing simultaneous measurements of small scale and large scale at the same time. That's what the dense array observatories would give you in the future. So that's sort of maybe a next step, is getting that cross scale measurements simultaneously. We'll have to build that up statistically with GDC. But again, we're comparing this to previous missions where we have a single spacecraft. So this is a huge advance. Any questions about that? It's kind of important. Yeah.
So you said small scale. I probably close it again. Tiny small scale.
Right. That's great. So each spacecraft is going to measure at very high resolution along its orbit. So that's probably even a kilometer, say, scale. That's in the ground. Sometimes 1 to 10 kilometers scale. But then, and then we can have 2 spacecraft within something like it's 20 seconds. It's 150 kilometers easily interact. Swarm has actually done much better than that. So we could get latitudinal measurements on the order of 100 kilometers, 10 kilometers. Right now, longitudinally, we are currently starting our science phase with sort of a minimum separation of 300 kilometers long. Now that could be adjusted. That's what we chose based on minimum fuel use. Okay? But if there's another scientific reason to spend more time, or even a smaller separation, we can do that. We could probably get down to 50 kilometers. I think Swarm is like 50 kilometers. Smaller than that, it starts to get really complicated, because then you have to worry about running into each other. But they might even have done 4 kilometers. I mean, Swarm did something very, very cool. They were doing like 4 or 8 kilometers for a while. So one of our goals is to talk more to Anya Strong and those guys and learn more about how they're doing it cheaply without having to. They have a system where they kind of autonomous. They don't have a lot of people in the operations center every day joysticking the spacecraft around. They've got a pretty good system. So this is where we are now, but I think there's room to kind of shrink the constellation if that's what makes sense for the science. But also, we want to go to larger scale. We'll just do that. That's fine. That's an area that's kind of currently being studied, is how close we get. Okay. So the science objectives were actually laid out in this science technology definition team report, and they had the 2 goals. They actually laid out 10 objectives, and they sort of ranked them by how important they were. They had a category called core, which was the most important. That's objective 1.1, which is how are thermospheric neutral winds at high latitude, how are they driven? How are they driven by a combination of electrodynamic energy input and kinetic particle precipitation input? So that was viewed as the most important. Second tier of important we called core comprehensive. And it's the next 2, how are high latitude plasma density structures like polar cap patches, how are those developed, how do they form, how do they evolve, how do they propagate? And then 1.3 is the same with neutral density structures. So we know that they're kind of more or less stable, but maybe dynamic neutral density enhancements at the cusp, in the rural zone, various places like that. And we want to understand, are those driven by precipitation, are they driven by winds, are they driven by collisional heating? And so those 3 objectives were viewed as 3 of the most important, along with the next 3. So remember, the first goal is about high latitude energy inputs and responses. The second goal is about the global redistribution. So I think kind of the fun thing about GDC is it's going to look at these low and mid latitudes as well as the high latitudes. And objective 2.1 is usually think of the magnetosphere as being insulated. The low and mid latitudes are insulated from the magnetosphere. And that's true in the very long time average, they're insulated. But for rapid variations, either on time scales of seconds to minutes, to tens of minutes, and then again, another process on time scales of hours, you can have the magnetosphere either directly impact the low and mid latitude or through an indirect wind-driven process impacting. So objective 2.1 is understanding to what extent rapidly varying electric fields in the magnetosphere can penetrate deep into the low latitudes and drive plasma density variations. And then to what extent do heating put in the high latitudes propagate to the equator and drive strong winds, which then drive wind-driven dynamos and drive electric fields, which drive plasma density variations. So we're really looking at those two different pathways. And this also includes some suborbital physics and some also regularity formation. Sort of a lot packed into that first objective. We have objective 2.2, which is about how traveling ionosphere and atmosphere disturbances are formed, how are they evolved, what's the relation between those two phenomena, how do they propagate, and that's what we're going to be studying with objectives 2.2. And then 2.3 was the last of the very highly rated ones by the SDT, which what are the drivers of these vast chemical changes we see, chemical composition changes we see at low mid latitude. Again, this region is not chemically mixed, it's stratified by molecular mass or atomic mass. And so what happens is at times you get a lot of heating that causes nitrogen-rich gas to upwell to high altitudes, and then that changes the ratio of oxygen to nitrogen. It changes the recombination for plasma density, and then the chemistry of the regions change whenever we have these regions. What we see are these big tons of nitrogen-rich gas or oxygen-depleted gas extending down from the high latitude regions, and we don't understand what drives that. There were three other objectives. We're able to do one of those three lowest priority objectives. It's called Hemispheric Asymmetries, and that's really understanding the two poles are not the same. We have very different magnetic fields. The magnetic field in the South Pole has a little bit different geometry, multipolar character to it. We have different land cover in the two regions. We have different seasonal variations, obviously, between the two hemispheres. And so those things all combine together to give you potentially very different pointing flux into those regions, very different responses, very different conductivities. And ultimately that will impact the magnetosphere. The magnetosphere itself, we kind of treat the two hemispheres equally in many models these days, although that's changing. We want to understand the differences there and how that might modify, say, ion outflow or conductivity or all these other feedback mechanisms that drive the magnetosphere. There are three other objectives which are not listed here, and the reason is because we tried to do them in our implementation, but it just became too expensive. So you needed kind of a different set of instruments to do it. And these were all done by the same instruments. And the other three objectives needed additional instruments. So within the budget that we had, we couldn't do it. But headquarters suggested doing the dynamic mission, and we'll talk about that. But that's another mission recommended by the decadal survey that is going to look at, again, those remote sensing techniques, to look at the altitude variation, perhaps the spatial variation, looking down, and trying to get at really the detailed mechanisms of how the lower atmosphere forces this upper atmosphere region. So we're looking at really solar and magnetospheric forcing to this region, and dynamic will look at the lower atmosphere force, which is kind of the third leg of the triangle. All three are very important. You can't understand the thermosphere without understanding the solar input through ultraviolet, or the magnetospheric input by electrodynamics, or the lower atmospheric forcing through neutral dynamics. And two of those objectives will be done by dynamic. There's a third one about cooling, which dynamic may cover, or unfortunately may have to leave it out if dynamic does not cover. In addition to the science, I mentioned this Living with the Star mission. We're going to have these space weather effects we're going to be studying. Really, we're doing the science of these space weather effects, and then that can be used in the future to drive the operational models and our understanding. Primarily, those include thermospheric expansion, the orbital drag on these satellites that is highly variable and not predictable to a great extent at this time. The radiation environment in space and at aviation altitudes can be measured by these spacecraft. Charging of spacecraft, radio wave propagation effects, and then geomagnetically induced currents. The currents that are induced in pipelines and power grids are formed in the ionosphere thermosphere, and GDC will give us some understanding of what are the causative electrodynamics that drive those currents, then cause damage to the pipelines. So space weather, we're not a space weather mission like SWIFO or ACE, not ACE Discover, but we are planning to provide some space weather data for people to use, but also science results that and model improvements can be used to better understand space weather. I won't go through a lot of this, but I'll send you these slides so you can have them. But the GDC status is essentially 2018, the SCDT started, they sent their report in 2019, and then we spent a year trying to do an implementation study to see of the SCDT, what could be accomplished. Then once we did that, we got the go-ahead from headquarters. Headquarters released the Instrument AO, the IDS opportunities, so people could compete for those. And then headquarters selected the interdisciplinary scientists. So I'll talk about those. Those teams are in place through the end of phase D in NASA speak. That's 3 months. That's launch plus 3 months of commissioning is phase D. So they'll be there developing tools, developing models that will end at that point. At some point before launch, headquarters is going to compete an additional set of IDSs, interdisciplinary scientists, to work in the science phase of the mission, the archiving phase. So that's just wait for that, but that'll probably be something like 5 years from that. Competition. So the IDSs are in place. I'll talk about their work. The investigation is still in process. We thought it'd be finished by now. It's not quite finished. We've got some very capable instruments already, and then I'll talk about those. And we're still waiting for the end result, which is expected toward the end of this year. And we're waiting to see about a magnetometer and a thermoplasma instrument, and that we expect to get one of each of those by the end of the year. We're basically working now, as I said before, to kind of take all these separately proposed investigations and marry them together, along with the SCDT recommendations, and marry them together to a design that gives as much science impact as we can, and does as much of the SCDT recommended science as we can. And we're working to get all that set up and get confirmed by NASA by the end of 2024. By that point, we'll have a launch date, we'll have an official budget, we'll have an official schedule. So by the end of 2024, things that are kind of TBD now will be a lot more nailed down. It's one of those TBD things when we launch. It's TBD, but we're targeting 2025. For those of you who've been following the NASA news, there's an independent review board on GDC. That's standard process for all large missions over $1 billion. They're held early in the mission life cycle just to make sure that we're on the right track. And thanks to those who served on that IRB, that's very helpful. Really kind of gave us confidence that we were going in the right direction, but also gave us some nice suggestions on how to improve things. And so that report is expected to be released imminently, and NASA will have a little response to it saying, hey, here's what we plan to do in response to that report. For sure, it will be discussed at the Heliophysics Town Hall that Nikki Fox is leading on October 24th. They'll also talk about the dynamic AO at that time. So probably it will be released before then. I was expecting it already. There's just some hold up with the press release. But once they have that, it's going to be publicly released. You can read the report, you can read NASA responses. If you have questions, feel free to ask. We can try to answer those. And then you can bring your questions to the town hall as well. I just want to point out a couple of things is that we were very happy to see all the white papers that were recently submitted. There were a lot of white papers on ionosphere, thermosphere, mesosphere work. And a lot of them were calling for measurements that GDC would provide, and a lot were calling for measurements that Dynamic would provide. The great thing about that is NASA really wants to fly GDC and Dynamic together. So by getting that strong community support, we can have this multi-point direct measurements and the remote sensing measurements, and together solve the whole problem, at least attack the whole problem in the proper way. We're looking at a way to get GPS RO instruments on the spacecraft, and we will also include a low latency, several minutes space weather stream that will just broadcast continuously the current status of space weather in the atmospheric atmosphere system. For those of you going to AGU, we have presentations and posters on Tuesday, and of course, relevant sessions all week. Many of you are leading those sessions, so I don't need to tell you about those, but there's a lot of great GDC and dynamic relevant science going on. And just a couple of notes, there's an AGU Living with the Star Town Hall on Monday, and then we're going to do a GDC Town Hall Thursday of AGU. That one isn't fully confirmed because I haven't got the room yet, but they're working on scheduling that. And there'll be a student early career Q&A panel afterwards. And that'll be advertised in CDAR and SBA stuff. So I won't go into the 6 identical instruments. I'll go into the instruments in a bit. I talked about the competitive phase A. For the orbits, they're high inclination. We want to get up reach all the geomagnetic latitudes and reach as many geographic latitudes as we can. And sort of a sweet spot is about 81 degrees. If you go too high, then you are kind of locked in, as Dynamics Explorer was, always seeing the same local time during the same season. We want to get variation of season and local times. We want a little bit below 90 degrees. On the other hand, if you go too low, then you don't get to fly over the full range of geomagnetic latitudes. You don't get to fly over important ground-based radars and so on. So 81 is about a sweet spot. The orbits will be nearly circular. Circulars, we can make them in that range, and that's just to simplify the data analysis. For example, by keeping them close together in altitude, we will not have to correct as much to normalize their pressures, and we can measure even weak horizontal pressure gradients in that way. We'll have onboard propulsion, so we'll be constantly boosting them to make sure they stay in this altitude corridor, and also slowly adjusting their spacing so we can kind of keep the sampling the way we want. And with a 3-year prime mission with 2 additional years. I think this slide is very important because it's something that we're trying to get across, and I'm not sure we are getting across. But often these missions, especially the smaller missions, they're not really community missions. They're built by some group that they can usually compete for the ability to do that, and they're built for NASA, and they maybe share their data. These days, the data is shared, but often they're not really a community-driven mission. They're driven by a science team, which was selected by NASA, and they do their things. And the best ones of those will then invite community members to contribute, because that's how you make a really strong mission, is by getting diversity of input and really leveraging everyone's effort. Because GDC is a directed mission or strategic mission, we want to build this from the outset. So we think the best way to do the science, there's no single group of people, even a relatively large group, that knows everything, that has all the skills. And so the reality is our community is very broad and very, very diverse. We want to be able to plug community members in where they feel like they fit in the best and serve as sort of an anchor or a hub for synergistic opportunities. So even if you're not getting direct funding from GDC, you can use your connection to that hub to advocate for, say, NSF funding or NASA funding outside of GDC or NOAA funding or whatever you're looking for, international partner funding. The idea is we want to be that hub that really makes it possible to expand the community a little bit and get those additional investments, because by leveraging GDC, hopefully everyone else can do more of their own science, and then by doing that science, that will help GDC also. So it's kind of a two-way street. We really want to make sure that people feel this is their mission. I know it's been kind of quiet up until now. That's been because of procurement rules. Those rules are now relaxing, so we really want to get community input, engage people, start brainstorming together on the best ways to maximize the impact of this mission, but also how best to use it to maximize other things that you want to do. This I won't go into too much. I guess the last bullet I just want to say, we have currently, I think, a fairly strong community given the history of how the NASA funding has gone in this field. But it's only recently that NASA has started putting significant funds into this with timed ICOM gold. And we haven't had a strategic mission in 20 years. Time is the last one. And if you look back to in situ sampling, it's been 4 decades. So that's a long time. And of course, people retire, they move on, they pass away, unfortunately. And so we really want to build all across the career pipeline, but especially early career, we want to build and sort of recruit and retain and strengthen that group so they can lead the next generation. Just to show you where we are now. This is the first meeting we had back in May. We're having closed science team meetings for the first 2 years. That's only because we aren't even under contract, some of the teams, and we're not really formed yet. But as soon as we have everyone plugged in, under contract, ready to go, we want to open these meetings up and have community participation in the science team meetings, community suggestions, get brainstorming on how to collaborate and that sort of thing. And that will probably occur in early 2024 once we get everybody set up. This is the current community involvement in GDC, and I highlighted UCAR and NCAR because I think that's really great that you guys have already some participation. We'd like to see more participation from NCAR and UCAR. We've talked a little bit about how to make that happen. But of course, there's a wide range of teams. There are more teams who are in the competition who will, at least some of them will appear here at some point. What we'd like to do is get this as representative of the community as we can. and maybe reach out to groups that aren't on this list and try to engage them to the extent that we can. Okay, that skips sort of the intro part, and I've got some technical stuff, but I just want to see if there's any questions about the community nature of the mission or what we're trying to do, how we're trying to form it as this hub of other efforts. I'll give you an example. Wenbin Wang asked a nice question earlier about using WindCube, which is a CubeSat to measure the wind in the thermosphere, I guess by remote sensing in that case. And so, you know, he pointed out, hey, there's going to be a lot of these other missions like CubeSats, like in the space station observations, ground-based observation, maybe other satellite missions. How can we work together to leverage that? So that's an example of how we see GDC as a hub. We try to publicize as much in advance what we're going to do, how we're going to do it, take community input on that to try to make it as useful as possible. But also that lets people go off to their funding agency, which could be also NASA outside of GDC, and say, I want to fly this CubeSat. I want to build this ground-based. I want to develop this model. Here's why I want to do that on its own. And here's why you wanted me to do it, because it's going to fit into GDC as well. It's going to maximize GDC while maximizing our other. So I think that was a nice conversation by Wenbin. I think we also want to do sounding rocket missions, you know, kind of across the board. There's a lot of different opportunities to leverage GDC and get even more science out of what we're doing. We talked a little bit about how we're doing this. We're going to be measuring in this narrow altitude range, and those of you who know a lot about this more than I, perhaps, most likely, recognize the problem with this is that we're measuring this altitude range, but of course there's a lot of vertical gradients with different parameters, and those parameters, basically all the parameters, have strong gradients of altitude. Some of them are stronger than others, and so, for example, the neutral wind here is one component of the neutral wind with altitude. And you can see that once you get below a certain altitude, this is a model run from the GITA model done by Jared Bell, the gradient and the shear, I guess you might say, in the wind becomes very strong with altitude. So GDC will not measure, GDC will measure here, we'll extrapolate down to some reasonable altitude. But below that altitude, we really rely on modeling, ground-based observations, and missions like Dynamic to really understand. I think that's what I was trying to say, is that GDC and Dynamic together is providing the full picture. On the other hand, you can do an awful lot with measurements here, extrapolated in wind here. You can extrapolate some of the neutral density and composition measurements a bit, and the energetic particles and electric fields at high latitudes can be extrapolated also down. So we kind of see that we get maybe a bit of an altitude profile here, not all the way down. This critical region down here will be covered mostly by Dynamic. And so what I've shown here, Jared has calculated, for example, the ion drag force. And so we're trying to understand what drives winds. Those are driven by some combination of viscosity, Coriolis force, ion drag force, and pressure gradients. And here's one of those four terms, one of the vector components of it. And what he's showing is that there are 4 local times. Red is dusk, yellow is noon, blue is dawn, and black is midnight. Previous missions would only have measured one of these 4, or maybe 2 of them at any given time. They measure a ascending leg of the orbit and a descending leg. With GDC, we're going to measure all 4 of them. We'll actually measure at 12 different local times, so we'll kind of be able to fill in this, populate this region and understand the detailed variation with local time. But again, we won't have that vertical information, so we'll have to rely on some other measurements for that. But on the other hand, you can kind of see that if you're measuring here, at least in this case, you can estimate the forcing to within 20 or 30%. Maybe there are other cases where it's worse, but here's a case where even with just this information, you're not doing too badly. Whereas if you were to measure only here, you wouldn't have any idea what this force is. So that's why we kind of do it really good. One of the challenges we have in measuring those, estimating those drag profiles, is understanding the neutral density and composition below you and the plasma density. And so what I'm showing here is some, again, get-in runs from Jared that show the altitude profile of the neutral density at a certain location versus time, and the same with the plasma density. And you can see the neutral density is variable. It has lots of interesting spikes. If it didn't, we wouldn't want to measure with GDC. But typically, it's pretty smooth and pretty well behaved and somewhat coherent from moment to moment and so on. The plasma density, because of the nature of how it's formed, during the day, it's probably easier. At low latitudes, probably a little easier. But once you get to nighttime or energetic particle precipitation, you get all this different structure. And it's very hard to say what the detailed density profile is going to be. So we estimate this. I'll show you how we do that. I plan to do that. This we probably going to have to measure or get from other observations. So how do we get the neutral profiles? Jared has done some forward modeling work where you take the measurements from the mass spectrometer that also measures the temperature and the density, and you fly along through here and you make a single point measurement here, and then you assume like a temperature structures like that given by EMSIS, and then he tries to propagate down what is the mass, the temperature and the total neutral density, and you can do it over a certain range. After a while, the area gets larger, but you can kind of estimate, at least over some range, what the neutral column looks like based on your really comprehensive measurements of mass, composition, temperature, and density at a certain altitude. The same is not true of the plasma density, and so we are relying on multiple schemes. One, as Dan Solomon is maybe on the call, he's going to be helping us out by modeling the electron and ion input that we have coming into the atmosphere, and then using that neutral profile to get an ionization profile. But of course, transport and lifetime effects really change that. So at some point, you have to rely on either ground-based measurements, modeling, or what we're hoping to do is a GPS radio occultation type measurement like this stuff at Cosmic that Nick is familiar with. And we just, some combination of those will give us this plasma density. So you can kind of see the issue. And then if we're flying with dynamic will maybe also measure that vertical profile. So it's hard to do it all with a single mission, and we're hoping to the combination of those missions plus the ground-based will give us kind of what we need. The other advantage here is that we have missions like Cosmic 2 in this case, and then Spire and some of these commercial radio occultation missions that are starting to get dense coverage of radio occultation in this region. And so they can also provide some information about what the density profile looks like below GDC. I'll share this slide with you guys. This is just a table, a bit of an eye chart that shows all the parameters that we're measuring. It's basically all the energy inputs, all the responses of the neutral ionized gas, what the sample rates are. You asked me about the one of the other aspects, the resolution, precision, accuracy, and so on. These are the expected performances. Right now, the instrument requirements are a little bit looser than this. This is where they currently believe they'll be able to reach. So you can see it's pretty decent accuracy. They're getting down to several meter per second accuracy in the ion velocity and the wind velocity. And you can see just the sort of range of temperature, accuracy, and so on. And then I've sort of mapped here what instruments are doing what. We'll talk about the instruments in a second. But I just want to point out, we don't know what the magnetometer or thermal plasma instruments look like yet. Headquarters tell us. We can more or less assume the magnetometer is going to measure this magnetic field parameter. But there are some unknowns about which thermal plasma instrument there will be and what it will measure. So I put some TBDs here. I mentioned the instruments. This is the first instruments led by Lila Anderson, just down the street. She's at CU last. And Ether is basically a direct outgrowth of the MAVEN LPW instrument. You've studied MAVEN data, some of you have done that. This is a linear probe instrument with two booms that extend the linear probe out beyond the perturbing effect of the spacecraft. That will measure the temperature and density of the electrons. They have a complementary technique called thermal noise reception, thermal noise spectroscopy, which also measures in a different way, in some ways more precise, the density of the gas and the temperature as well. Then they can also measure things like small scale irregularities and also plasma waves. So this is Ether. Those are the different things it's measuring. And if you want to dive in, when you can see these slides up front, you'll be able to see the details of what they expect to measure. CAPE is a instrument led by Dan Gershman at NASA Goddard, and it is a top hat electrostatic analyzer similar to, let's just for an example, like DMSP sort of energetic particle measurements. These are measuring the precipitating and upgoing or secondary electrons, and then the precipitating ions. And those are in a range of like 0 to 30 keV for the electrons, 0 to 40 keV for the ions, and they get pitch angle distributions. And the purpose of this is to really understand the energy inputs, but also the energy spectra, the details of the energy spectra that can give you ionization and heating at different altitudes, conductivity changes. And I think this one has an inherent resolution of about 50 milliseconds. So it's doing something like 20 samples every 10 kilometers, about a 500 meter scale. And they may or may not be able to send all of those measurements down to the ground, but that's their inherent resolution. It's 50 milliseconds. So we're getting very high resolution along the track of the spacecraft. This is the Mosaic Instrument that is here, and this is led by Mehdi Bena at UNBC. This is very similar to the MAVEN NGIMS instrument or the DE2 Watts instrument. It's a mass spectrometer, very capable mass spectrometer that can measure with 1 AMU resolution. We haven't really flown mass spectrometers in Earth's orbit in a long time. We had AE and DE, and to my knowledge, those are the major ones. They had very good mass spectroscopy, and then we stopped doing mass spectroscopy on Earth. We're doing it at Mars, we're doing it at Venus, but it hasn't been done a lot recently. And so a lot of our models don't have the full range of, say, solar energy input or magnetospheric energy input to see how these compositions change under those conditions, or how they might change under lower atmospheric force conditions. So I think having this mass spectrometer just by itself will give a wealth of information about how the composition of the atmosphere changes. So they're doing ion and neutral composition probe. They turn the filament on or off as they want to study ions and neutrals. They do that every 2 seconds. They cycle between. Also in that 2 seconds, they do another kind of measurement, which is they have these baffles in front. They're like little windshield wipers that just go up and down. And when they block the gas flow should be coming in this direction as the spacecraft moves. But sometimes it'll be coming a little bit off if there's actually a wind in the gas. As they move the windshield wiper, the direction from which there's a minimum in the signal tells you what direction the wind is. And the width of that tells you the temperature. So they can do that for the neutral and ionized gas as well. So this instrument provides a lot of different measurements: neutral wind, neutral density, neutral temperature, neutral composition, and the same for the ions. And every 2 seconds, they're making that full suite of measurements. I'm particularly excited about this one too, because it'll make measurements of other species. Xinjiao Chu has shown these very high altitude iron layers and that sort of thing. This one can measure iron. If there's maybe 300 feet long, is a little bit high for that. But if there is a tail of some of those long plumes that reaches up that high, they might see it. They're pretty sensitive. They can do a lot more of the chemistry with the N2 and the N1. So. Also things like helium. Like they're not going to measure hydrogen, I don't think, but helium is pretty important, pretty understudied. So that's a great instrument. Any question about the instruments? The other instruments, the magnetometer I think they're pretty standard. They might be different complexities, but their job is to measure the vector magnetic field to see where the electric currents are and to see where the alpha activity type waves are, ULF waves. The thermal plasma instrument, I'm not really sure. There are multiple options there, but some aspect of the thermal populations, or the superthermal populations, density, temperature, and so on. So complementary to Mosaic, probably more specialized in the ion instruments. How do we do it? I mentioned this idea of having these multiple spacecraft separated by a baseline. If you have one spacecraft and you fly and you see a bump, you don't know if that was a pre-existing bump that you flew through and that stayed there before and after you reached it, or if you were flying along and then everywhere there's a time variation that changed over time and then went back down. You don't know. As soon as you get more than one spacecraft, you can start to remove some of those ambiguities, and you can start to understand the difference in spatio-temporal variations and also in latitude, longitude, and time variations. And it turns out by having 3 spacecraft, you can measure instantaneously the longitudinal and latitudinal gradient. And then if you have 4 or more spacecraft, you can also measure the time. And so we have just conceptually these different, sort of triangular baselines that we put together, and we can combine those to make time variations. And you can see there's a nonlinear effect. The more observatories you have, the better it is, the more unique baselines you get. So it's a N choose K problem. As soon as you have 6 observatories, you get 20 different baselines. And that's how we can better refine our understanding of what's happening. We can kind of use those different separations to understand the gradients at different scales. Of course, we really do benefit from ground-based maps. So we're hoping to have IceCat 3D up and running at this time. Hoping to have some additional high-latitude all-sky imagers and Fabry-Perot type instruments, magnetometers, but also, very importantly, low and mid-latitude. I think this is an area where we don't have as much in the U.S., as much instrumentation in this area. There is some, of course, at Ikamarka, there's radar, there's imagers in Asia sector and also in South America. There probably needs to be more done there. But again, because GDC is a global measurement, we're going to want to compare to measurements of low and mid-latitude as well. So this is very important. The incoherent scatter radars, the cameras, and so on, give you those extra pictures, both of altitude variation and also horizontal variation that are hard to get with the direct measurement. So this is really something where, again, this is an option for people who are getting funded from NSF or maybe other US funding agencies, ONR, to say, I want to do X science, I need these observations. Oh, and by the way, this is also going to benefit GDC in this way. Let's invest in that. The key is we want to be able to enhance someone's sales pitch, I guess, by showing how they will also benefit GDC in addition to doing their own science. That might be a help as we put it. And then we have international partnerships that we're working to try to get Canadian groups, South Korean groups, and Japan and so on to contribute their own investments that they're doing for their own reasons, but to kind of coordinate it together to make the data useful and accessible to everyone. I mentioned the orbits. This is how they look. We start actually even closer together than this. We have 6 different orbit planes. Each satellite is its own orbit plane. They start out in the same plane, more or less, and over time they spread apart. This is sort of early in the mission where they're measuring what we call local scales, which is several hundred kilometers. Later they spread to regional scales. I don't have a picture of the regional scale, but eventually global scale. And you can kind of see this is I don't know if this is the final global scale. I forget what day of the mission this is. But you can kind of see we get to spread across different local times. This is how it might look with all the satellites synchronized. Of course, we can also change the phasing of the spacecraft. So right now we're showing all 6 crossing the same latitude at roughly the same time. But we could instead have conjugate measurements where we have 3 in one hemisphere and 3 in the other to try to understand the asymmetries in the hemispheres. We do something similar to look at time variations on like tens of minute timescales, where we have a set of 3 spacecraft and then following behind another set of 3 called the follow leader mode. And this is an idea of how we can try to measure things that might be like thermosphere heating, thermosphere chemistry changes that might take 10 or 20 or 30 minutes to go faster than an orbit. So you want to resolve it suborbital period, but slow enough that if you just had one group of spacecraft moving together, you would resolve it, you move on, and then it would change after you've gone. So we want to look at different ways. And here we're looking for clever ideas from the community also, how best to optimize the sampling to study different scientific phenomena. We can easily change the phasing within orbits, and we can change the rate at which we spread, things like that. So there's a lot of unexplored phase space here, I think, for improving things. Any questions about the orbits? I think that I'll show you later a link where you can download the predicted ephemeris as it stands right now. But again, that's not the final. We want to hear from people, and you might say, study this phenomena. You really want to be studying at this scale, this season, at this location, and your ephemeris don't do that because you're not phasing it right or you're not whatever. So that'd be really cool. You can download those ephemeris and then run through your model or just look at them and understand them. I mentioned the IDS teams. I'll just try to go this quickly. There are 3, and each team has 1 or more co-investigators. So the first is led by Rebecca Bishop at the Aerospace Corporation. She's leading a project called Adaptive, which is really a tool to make the GDC data readily accessible to everyone using a common tool. Of course, you can still use your favorite tools, which will always export it to whatever you want to do. But this is a low friction way for people, especially new to the mission, to get started. It's also really cool is the thing about it is to make the visualizations very high quality out of the gate. And one of the secret sauce that Rebecca brings to this, besides her scientific expertise, she's working with Tad Gilo. He was a former computer animator at Disney and Sony, and so he has a lot of, sort of the back end side of how they make all their code and trying to make this interesting. So it'll be a data access, data analysis, data visualization environment that we can make it as open as, and also the source code is to be open, so you can go and write your own modules about the use of it. Yue Deng has a team mostly at University of Texas, Arlington, but of course she has other collaborators at MIT, Aerospace, Michigan, and APL, and also Colorado. And that's her team. And she's doing quite a number of things with a larger team. She's one of the co-founders or co-developers of GitHub model, so she's working on some major enhancements there, upgrading the grid, changing the forcing, including the mesoscale, adding soft electrons, pulling it back into the SWF framework, and so on. So a lot of different model enhancements, and I think that's a great example of what this mission can do is invest long-term in model development. We have, of course, GitHub is not the only model. In fact, GitHub has strengths and weaknesses like every model. And so we might want to look at how can we enhance other models in a similar way so that 10 years from now, when we're looking at the data, we can say, oh, okay, the state of the art get them and the state of the art this, they give different results. Why is that? So we have scientists like Li Ying on here and others in the team, UA and others, who can maybe bring that to bear. But we might need to do a little bit more work to go beyond the GITM. I think we've got plenty of GITM, but maybe not a lot of people working on other models. They're also doing some interesting tools, some artificial intelligence machine learning that's kind of interesting to do sparse data and reconstruction of sparse data, and then helping us really define the mission. And they're developing some data products for joule heating and convectance. A lot of ground-based work too is very important. Jeff Thayer's group at University of Colorado is this group here, one's in Colorado person. And they have a number of objectives. I won't go into all of them, but one of the coolest ones is this, they call it GNSS accelerometry. So for those who are familiar with CHAMP data or GRACE data, where you're looking at acceleration and deceleration of the spacecraft, they have a sensitive accelerometer of the spacecraft that can tell when it's hitting a pocket of higher neutral density or low neutral density, and they can sort of see what those nano-G changes in acceleration are, and use that to infer wind density, temperature, etc. We don't have that on GDC. Those instruments are fairly expensive, fairly resource intensive, and just we couldn't accommodate. But GDC, like most spacecraft, will have a GPS receiver of some kind, even if it's not an RO version. And they're going to do a detailed study where they have a complete model of the spacecraft, including the surface composition, the surface temperatures, the attitude of the spacecraft at high level, and so on. And they're going to use the precision orbit determination to get essentially a poor man's accelerometry. They're going to validate that. And they're going to validate against the Mosaic measurements, use the calibrate Mosaic, and you can just they're going to use that to feed the data simulation models. So this technique, if they can get it working, could then be used with other spacecraft that have GNSS receivers, but not accelerometers, to kind of expand their databases on thermospheric properties. So that's kind of interesting. They're doing a lot more. I just didn't have time to share it. So in summary, I guess it's a community mission. I'm very happy to be here talking to working with the community. Really want to start strategizing on how we can, with a little bit of extra investment or a little bit extra work or proposals to other funding agencies, how can we strategize together to find those synergies that would really be low-hanging fruit that really help us move forward. I want to thank people for the community endorsement letter from CDAR. This was extremely helpful. Here's the link for the latest ephemeras, which again, you can have these slides and let you get the latest predicted ephemeras there. How to connect, we've got AGU in fall 2022. We've got a dedicated Slack channel. The only thing I have to apologize for is that the Slack, it only lets you have a link, invitation link for like 15 days to the free version. So this link here is valid till October 26th. If you click on this on October 27th and it doesn't work, just tell me. We'll send you we have to figure out a better way to do this so people can just join this whenever. And we'll be advertising this again. We advertise it on CDAR and SPA will do some more of that. And then we have right now a blog, which is going to be updated, and there's a mission video. So that's the basics of GDC. There's a lot more, and I encourage you to come to some of the posters on Tuesday at AGU. You can talk to the individual PIs, the IDS PIs. You guys have the lucky that you can go down the street and just talk to Lila and Jeff directly, or your local experts, Li Ying and Stan, who are on the team, and just sort of see what's latest and we can always share them. Any questions? All right, well, I'm pretty excited about this mission. So thank you for having me, and thanks for coming. And I just hope we can keep this discussion going, find better ways to work together. Of course, absolutely. I should have said that on day one. I should have said that. We need postdocs badly. We need early career scientists also of all kinds, all sorts of students as well. So absolutely, just send me an email. I can put my the whiteboards. Definitely. And we have a lot of science team members at different institutions. So we're looking for postdocs at Goddard, but also we have different institutions who are involved, and probably they're all looking for postdocs. So depending on what your interest is and where what your research topic you want to look at, there's probably a home for you somewhere in one of those places. All right, thanks.
Any other questions? Questions from online?
So how did we come up with 6 satellites?
Okay. It's a question near and dear to my heart. The decadal survey came up with 6 because that divided evenly into 24 hours of local time. I think. I mean, I don't want to be flip. I don't want to be flip. But I think that's what they. Okay. But it turns out they had a good intuition. Maybe they did more than that. I don't want to joke. But I mean, it looks reasonable, right? If you have that. When we do the detailed analysis, as I said, you need 4 to get instantaneous separation of time and space. And when we did that, we said, okay, if we want to study, we could do it with 4 spacecraft. The 2 problems with that is, if you want to study all these scales from local to regional to global, and in each case you want to study all the seasonal variation and this local, you need like a 5-year mission. Because we were constrained of a 3-year mission for funding reasons, and also because spacecraft that live 5 years are way more expensive than spacecraft that live 3 years, we had this other constraint of doing a 3-year mission. So when you do that, you really need 5 spacecraft to do it in 3 years, not just 4. And then we said we could save more money if we make the spacecraft really cheap and get a 6th spacecraft and allow 1 to fail. So we're flying 6, believe we will have 6, planning for 6, but we designed it so that we can achieve our science with flying our full science. And our threshold science, which is a little bit below that. So we can do it for. They were talking about going to 8 or 12 spacecraft, which would be great. It wasn't 4. Yeah. I'll stick around if anybody wants to go up afterwards and have any questions. I'll share my email address and stuff like that. And I'll send these slides to your day.
Doug, for people online, Doug will send the slides to me. If you want them, send email to me, and I will share them. I don't want to send the whole.
Yeah, sure. Yeah.
So, contact me.
Yeah. And you could even type my email in the chat if you want. It's douglas.e.roll. Yeah. All right, well, thank you, everyone. And thanks, Cheryl, for organizing things. I appreciate it. 6. Actually, that's the other thing. We're trying to learn a lot of lessons from Cosmic 2, Swarm, other cube submissions like Snipe and SwarmX, and Easy is giving another example. Tracers, where you have these multiple spacecraft. And Swarm was actually written books about how to do multi-spacecraft analysis. I'm sure Cosmic 2 has also similar article. And it's amazing. People have done a lot of clever ways to pull information out of these multi-component dampers, for example. So we're really trying to learn from those. And if anyone here has experience with that, that's another thing we'd love to hear about is how, I know the Europeans have done a lot of this area, which kind of capture. They had cluster versus Swarm, kind of fun catch. Yeah. The interact wind, yeah, that's a great question. So I mentioned before how the baffles give you the other 2 components, the cross-track vertical and the cross-track component. The Mosaic instrument is designed with it's new since Dynamics Explorer. They have a retarding potential analyzer that will successively try to, they ionize the gas and they successfully ramp up the potential until they stop the gas. That's the ramp action assumption. So they can measure the interact with their RPA. That wasn't on DE2. They had a different scheme. They had a Fabric Pro that was looking ahead at getting a slightly different altitude.
You mentioned there will be additional IDS for this soon. What's the deal for the additional?
That's a good question. It will depend on our launch date. So the right thing to do probably would have it about 18 months before launch. That way they give the people that we have an overlap. We'd have the phase A through D IDSs. The new people would come in, they'd get a chance to ramp up, start planning, get used to the data. That'd be what I would do. It's about 18 months before launch. But we'll see headquarters on that.
So that would be like
something like that, yeah, 2027. So yeah, we'll be sure to advertise that. I think there will also be a guest investigator programs after launch as usual. But we really want to. IDSs are really nice because you get that long-term stable funding, and you can also just really dive into something a little bit more strategic than like what you usually can get out of a 3-year RNA.
This current IDS is that 5 years late already started now, right?
Yeah, they're not 5 years. They're actually the way their contract is written is they go until launch plus 2 or 3 months. So they actually got a long time. Yeah.
So they will only have they won't have data to work.
That's right. Almost all of their work is is tool development, model development, and developing algorithms to make data products, and like making plans for calibration and validation. So they're not, and there's also like Christine Gabriels is doing some work on interpreting all-sky imagery. So it's really tool development, product development.
Mm-hmm.
And then the phase E ones would be science. You do a science extension. Yeah.
Yes. The science. GDC.
Yes, yeah, or other data too, but yeah,
Yes.
yeah. And models. Yeah. So right now it's kind of model tool focused, and that will also be model focused, but also have science. Oh, we don't know the answer to that. I'd like to think it would be very high. About a year ago, we were lost together. That's still possible. We've heard the dynamic AO is soon. So they announced an opportunity, and that could be soon. If that's for the next year, we could actually align the schedules. They would launch together. Otherwise, I would like to think, they really want, they don't want GDC here and dynamic here. No, they want it together. Probably the most useful to dynamic is when GDC is a little bit more spread out. So I don't know, there's still value having the GDC in the early phase and having dynamic out. Probably the most useful is when GDC will spread to get that global picture for dynamic to also get there.
But is there any, the GDC is 3 years, but then there's an original 2 years possibility. So what's those 2 years? Is there a plan to possibly 2 years all the time, challenge with this kind of thing?
I'm going to be calling you and saying, what should we do? I'm serious. This is a community mission. Like we don't make it. What we do is we kind of find out what people think is the most valuable, what the most important. A current thought is we go 3 years with the 350 to 400, we spread out, and then one option is we stop the spread and we raise the orbits to 450, so then they can live a lot longer. They can live longer than 2 years. Or you could not stop the spread and just let them keep spreading and swarming. I think swarmers doing this, where they just keep spreading and eventually they wrap around and they get local again. You can kind of play that game. And then you save fuel by stopping their spread. It actually takes fuel. If you don't stop it, you get to save some fuel and use that for a longer lifetime. Yeah. And if the instruments are really sensitive, they can work you in 50 or 100 kilometers higher, where the density is like 10 times less, but still not much less.
So there really sounds like there's a lot more opportunity for GDC in the additional ideas in the and the GI and also extending.
Yeah, that's right. And then hopefully that's exactly right. And then hopefully we're planning to have a student collaboration, which would be a way to leverage students at multiple institutions, get maybe some fellowships as well as larger projects. That's one. And we're hoping to have some other programs where people can come in either as affiliate scientists or some things like that. We can have travel funding and have be part of the science team without a lot of funding, but with some. So that's all TBD. But I think we have a lot of ways that we want to again make this community mission, not just people who are officially on contract. So they can get involved in the planning. Well, it's easy to change things and make things better. But then B, have easy access to the data, the tools, same tools that everyone's using. It's not like the Solar Probe, because of the nature of the mission, those teams typically get the data and you don't get the data at the same time they get the data. This mission, we want everyone to kind of have the same footing to be able to make the discoveries and be able to motivate each other as well. And it's not going to be some proprietary.
And also this fuel, it's carried fuel for 5 years. But then after 5 years, the satellite can continue to fly still. Like a result of fuel, but it needs a longer time. So
it depends. The 5 years assumes that we're constantly boosting them until they back down. So if you stop boosting them, they just fuel. But if we boost them high enough, they'll take 10 years to come back down. So you could boost them high enough, run out of fuel, and they would just last for 10 years. At that point, we wouldn't be able to tightly control their orbits, so they might start to drift apart from each other. Yeah. If you're in global mode, you don't care if your satellites are slightly different phase, probably.
Yeah, because the kind of satellite is altitude and it has been like 2002 and it's like 2 years.
I think that is much higher. Yeah, because usually if you last that longer. It's
450.
Oh,
600. Oh, 600. Oh, starting from.
It depends on solar cycle. Yeah, Jim. We'd like to last a whole solar cycle, at least this. Because we're going to launch in that deep, basically the deepest solar. At least that's what it's like right now. So we'd like to get some of that solar mass. And what we're trying to be as conservative as possible in the fuel. And I don't mean not using it. I mean like putting conservative assumption on how much we need, so we can have some extra fuel to do the things we really want to do, which is last for 10 years. Make more missions. Yeah, that takes some, because the engineers don't like that. They want to, they want to make it as elegant and exactly what we want. Because they figure you spend money to build this things that you don't need. When in reality, we need 10 years. We're only doing 3. It's sort of the politically easy thing to do. It's my first time doing a mission like this, so I really welcome your guys' input. Really, just thanks for your time.
Thank you again, guys.
Thanks.
Thank you. Is it chunk?
Yeah, Swarm is raising. They